Our last speaker of morning session is Craig Knese from Washington University in St. Louis, and he's going to talk about the commuting pair of TTO and the local theory of stable polynomials. Craig, please.
Thanks very much. Thanks to the organizers for organizing, and thank you for inviting me to speak. So I thought maybe it was a bit of a practical joke to ask me to speak on truncated Toeplitz operators, but I took this as a challenge to say something about truncated Toeplitz operators, and it turns out that I know about this really interesting pair of commuting truncated Toeplitz operators that I hope to get more people interested in, because they do some really interesting things, and I hope this talk will also serve as some motivation for a recent paper that I did with Kelly Bickel, James Pascoe, and Alan Sola on a local theory of stable polynomials. So at the end of the talk, I'll talk about some of that stuff, but it'll mostly be an advertisement for Alan Sola's talk tomorrow. So there may be a little overlap, but I think a little repetition won't hurt. But so let's get into it. Or I wanted to say it's also nice to see so many familiar black rectangles and so many new black rectangles, but feel free to show your faces if you want to. You don't have to, but this way, if you fall asleep, I can take a screenshot of your sleeping face and save it for later. So, okay, so this is a story about rational inner functions in two variables, an associated pair of commuting truncated Toeplitz operators that you may not be familiar with. And then later I'll talk about how a local theory of stable polynomials is required to understand this stuff, at least in kind of the most interesting cases. So a lot of my talk is going to be focused on sort of old work, but I don't think that's a problem, because a lot of this will be motivation for this more recent work. And again, Alan will talk about it tomorrow. So this is integrability and regularity of rational functions in PLMS for 2015, which I guess is a long time ago to some people. It doesn't seem that long ago to me. But, so here's the basic setup. Rational inner functions on the bi-disk, which if you're more of a one variable aficionado, these are generalizations of finite Blaschke products. The setup here is I have a rational function, Q over P. So they have to be polynomials, and the denominator has to be non-vanishing for this to be analytic on the bi-disk, so the unit disk cross the unit disk. And to be inner, I need the polynomials to have the same modulus on the two torus. I mean, you could say something like the boundary limits are of phi are unimodular almost everywhere, but you can state it algebraically. So, and luckily there's a pretty concise description of all of these in terms of basically just the denominator or the numerator, however you want to look at it. So this goes back to Rudin and Stout, that every rational inner function is of the form p tilde over p, where p tilde is this, I switched to eraser, oops. The Apple Pencil will just switch me to an eraser randomly without my permission, but p tilde here is this reflection of p, where I reflect the variables, and then I have to multiply by a monomial of high enough degree to get a polynomial back. I do allow for like extra monomials, which you have to do. So this n1 and n2 just has to be greater than or equal to the bi degree of p itself in order to get a polynomial back for p tilde. And so the nice thing is this is a complete description of all rational inner functions. You can see that these are rational inner just because p tilde has this property very easily on the 2 torus, and then use some kind of like maximum principle. I didn't mention that these will be maps from the bidisk to the disk, and 2 important examples are just written here. So I write down, I don't know, the easiest thing I can think of that has no zeros in the bidisk, and I'll do 3 minus z1 minus z2. It has no zeros in the closed bidisk, so it's especially nice. And then you do a reflected polynomial and you get this on the top. But the fun thing that happens in 2 variables is that our generalizations of finite Blaschke products can now have singularities, as evidenced by the second example, which has a 0 at 1, 1, and I reflect it to get a rational inner function. So these are the basic objects of interest, and they're interesting because they generalize finite Blaschke products, but also because you learn a lot about stable polynomials along the way, which are these polynomials with no zeros on the bidisk, which I think are of wider interest too. All right, so there's a magical theorem that holds for rational inner functions on the bidisk, which is basically Aglers' theorem. But this really concrete form is like a culmination of lots of people looking at it from different angles, but I don't need to get too much into the history. So if I have a rational inner function on the bidisk, given all the setup earlier, it has this very special basically positive semi-definite kernel description that p bar minus p tilde p bar has this formula here. And I guess question 1 that I've written below is, why are these decompositions important? So I'll talk about that in a moment. But the point is, there's this great theorem that you can decompose the polynomial in this way, and K1 and K2 are going to be finite rank positive semi-definite reproducing kernels that they're polynomials in their 2 variables. I guess they'll be like anti-analytic polynomials in their second component, of course, but you have this nice finite dimensional decomposition, and maybe I'll steal something from the next slide just so it's clear here. If you write this all in the diagonal, the fact that this is positive comes from the fact that phi is bounded by 1. And one nice thing about this formula is that it basically gives you an algebraic certificate for this fact, because if you look at this on the diagonal, you can see that this is positive all from the formula written here, positive on the bidisk, I should say. Okay, so let me dive more into, so why are these decompositions important? How do you construct them? Are they unique? Can I describe all such kernels? So some of this, is more motivated than other parts of it, but I think after you study it for a while, you start to feel that it's this really fundamental thing that it really needs to be unearthed. So there's some really interesting ways to understand answers to these questions. So let's see. Okay, so why are these decompositions important? I already said the first thing. So the innerness property of phi gets expressed as an algebraic positivity certificate. So you see that it's an inner function algebraically, and that's great. These algebraic formulas also allow for other things like operator substitutions using something like the hereditary functional calculus. So here, if you have a commuting pair of contractive operators, you can plug them into the formula in a certain way, where you keep all the adjoints on one side and the operators on the other side, and get inequalities like this, which imply things like Ondo's inequality for commuting contractive pairs of operators. And then another cool thing you get out of these formulas are transfer function realizations, which generalize some familiar stuff from one variable that I can write out a really explicit formula for all rational inner functions in two variables as a formula like this. So the data involved is a unitary written in some block form, and this unitary colligation, where I have this diagonal matrix in here where I separate out the two variables. So Z1 times the identity in one block, Z2 times the identity in the other block. And then you form this unitary colligation. And every rational inner function can be represented this way with, I should emphasize, finite dimensional unitary. So a lot of this theory makes it really start to look like rational inner functions in two variables behave a lot like one variable ones if you have the right viewpoint. I mean, that's not completely true, but works out in many instances if you're careful about your theorems. So that's why these decompositions are important. And then I'll say a little bit about some of the history involved. So how can the kernels in these decompositions be constructed? If you want to go back, well, the history is a little convoluted, I suppose. Original proofs of like the existence of Agler decompositions for more general functions comes from a cone separation argument of Agler, which you can see like in Agler-McCarthy's Pick interpolation book. I guess around the same time as like Agler's original work, there's a paper by Kumert that basically does everything you need to do to get this like finite dimensional formula. It basically proves the transfer function formula directly, but you can go between a lot of these different things. So, so let me zoom in on some of these papers. So he has this, Kumert had a paper in 1989, synthesis of two-dimensional lossless endports with prescribed scattering matrix in the Journal of Circuit Systems, Signals, and Processes. And that constructive argument is great. And I actually wrote a paper kind of trying to lay out how I understand his almost elementary argument for constructing these kernels. But along the way, other people come up with different ways of understanding them, which is actually quite useful too, because it lets you dig deeper. So a lot of things I'm going to mention are done in much greater generality in this earlier work of Ball, Sadowski, and Vinikoff. That paper is Scattering Systems with Several Evolutions and Multidimensional Input State Output Systems in IEOT in 2005. They took a really general viewpoint and found Hilbert space geometry ways to produce these Agler decompositions for more general functions. It's such a general viewpoint that, you know, it still requires like work to get to more concrete cases. And so I think doing a lot of this just directly in the rational inner function case is interesting still. This is also closely related to this paper of Geronimo and Werdeman from 2004, and Kelly Bickel and I have done had a paper on inner functions on the bidisk and associated Hilbert spaces that lays out Hilbert space geometry ways to construct these kernels that fits the theme of the talk today. Okay. Okay, so I'm still talking about those Agler decompositions and the kernels that that encode innerness nicely and give you all of these nice formulas. And I'm just going to take it as like, I'm going to assume everybody's interested in this fact, and we're going to pursue it to its logical conclusion. So are the kernels in that decomposition unique? So the decomposition, again, on the diagonal was like this. You had these positive semi-definite kernels, K1 and K2, and basically like a sums of squares formula for P and P tilde. It turns out that these kernels here are not uniquely determined in general, and through examining this Hilbert space geometry approach to constructing them, you can show that they're unique in the rational inner function case exactly when the polynomial has a special property, which I've called saturated. The property that makes these kernels here uniquely determined forces you into a situation where P has a lot of zeros on the boundary. So where the rational inner function P tilde over P has basically as many singularities on the boundary as possible for its degree. And so the condition is that the common zeros of P and P tilde on the two torus, which you have to count using kind of the algebraic curve definition of intersection multiplicities, using resultants and so forth. This number of common zeros of P and P tilde on the two torus has to be as big as possible. It basically has to be all of the common zeros of P and P tilde on like the product of Riemann spheres. So I have this note here that the number of common zeros of P and P tilde on the Riemann sphere across the Riemann sphere is going to be 2 times n1, n2 in general. This is using like a product space version of Bezout's theorem. So people might be more familiar with a Bezout's theorem for like a projective space, but this is like a product of projective spaces, which is slightly different. So the formulas, you have to really hunt down the right algebraic curves book to find this, but we're basically saying that you get unique kernels in this decomposition exactly when P has as many singularities on the boundary as possible. So as an example of a saturated polynomial is this one earlier, P here, 2 minus Z1 minus Z2, its reflection is here, and you, just as a set, P and P tilde have one common zero on the two torus, but if you go through the rigorous like algebraic curve definition of intersection multiplicity, the multiplicity is 2, and this implies that this P is saturated because we have 2 times 1 times 1. And so this polynomial with this reflection will have a unique Agler decomposition. So that's interesting. But you want to, uniqueness is fine and all, and that's a very qualitative thing, but then you want to know like, well, if it's not unique, how do you construct the others? And is there anything interesting going on in the non-unique case? So again, I just wrote out the Agler decomposition here in case it's not at the tip of your at your fingertips. So my fourth question is, can all such kernels appearing in an Agler decomposition for the polynomial be described? I don't know about describing all of them. That's a little tricky because you can do things like, if you have one Agler decomposition, you could take a convex combination and get a new one. Those Agler decompositions obtained by doing that, or you can bump up like the rank of the kernels, and so it kind of muddles what's going on. So I'm going to introduce what I think are the most interesting kernels in these decompositions, and these are the ones of minimal dimension. So we can describe all of what I think are the most important kernels in these Agler decompositions using a pair of truncated Toeplitz operators that people may not be familiar with, which I think, kind of my goal of this talk is to get at least one person to write down their definition and believe me that they're an interesting topic. And there could be lots of things to do for more general inner functions in two variables. All right, next slide. Okay. So let me just define what it means for the kernels to have minimal dimensions, and then I'll talk about how to define these truncated Toeplitz operators I've been mentioning. So we let n1, n2 be the bi degree of p tilde. That seems a little awkward, but I need to keep track of the bi degree of the numerator and not the denominator. But the kernels in the Agler decomposition have minimal dimensions. This is either a theorem or a definition. You can prove that the lowest possible dimensions you can get for the kernels in such decompositions are n1 and n2. And that's the lowest I can get in the first piece and the lowest I can get in the second piece. And you can achieve that minimality in both pieces. And these are the interesting ones because, as I mentioned here, minimal dimensional kernels lead to minimal dimension transfer function realization formulas. So earlier I had this formula that I could write p tilde over p as this a plus b delta well, this whole formula here, and it's obviously desirable to use a unitary with as small dimensions as you can get. If you have like, if you're using a bigger dimension than you need, then there's this like extra fluff in the formula that the formula is not as useful when the unitary has bigger dimensions than in this case, the dimensions would be 1 plus n1 plus n2. So how do we describe all of these minimal dimensional Agler decompositions? So this leads me to Act 2 of the talk. And it's very easy to get myself stuck into deep technical waters, and I'm going to avoid it for the most part and just emphasize what I think is interesting. So let me start with just a couple definitions, and I'll try not to overload you with too many more. So I have a rational inner function, and this, what I'm about to write, works for other inner functions in two variables as well. I can associate a whole bunch of different Hilbert spaces to this rational inner function, but here let me just mention two. And both of these generalize the model space you might be familiar with in one variable, but in different ways. So here's one possible version of what you might call a model space associated to phi in two variables. I take two variable Hardy space, orthogonal direct sum phi times h2, and that's a perfectly legitimate version of a model space for phi. But here's this actually much smaller space that's going to be the most interesting to me, which is H2 intersect. I take phi times, and then this bar here is not a closure or anything, it's a conjugate. I take Z1, Z2 times the Hardy space and take a conjugate of that. So it's like, if you look at things in terms of Fourier support, this thing here with the conjugate is sort of living here in terms of Fourier support. And so I'm taking phi, and which is analytic, and sort of it should bump it up in some sense into places with positive Fourier coefficients, but then I'm intersecting with H2. So I like to think of kfee as it's sort of like a rectangular space, whereas hphi here is much bigger, because you can kind of think of it as the following picture. I have, in terms of Fourier support, stuff in H2 lives in this first quadrant. And if I do phi times H2 orthogonal complement, it's like your phi times H2 will kind of move me out, and then taking an orthogonal complement will remove stuff. So it's like I get an L-shaped space. And we'll see this quite literally when I look at a really trivial example later. But I want people to have some concept of just how you can have these two spaces which both generalize the model space from one variable, but they play different roles. So one thing I want to point out that's really important for what we look at is that this kfee has a really concrete description. It's equal to rational functions with p as the denominator, so q over p, where the degree of q, so this is by degree, and I'm using like a partial order on two tuples, on ordered pairs. The by degree of q is strictly less than the by degree of the numerator of my rational inner function, and q over p has to be in L2. And I have one proof in my talk, and it's like one implication of this. So why are these things in this space kfee? So the other direction is easier, but I did want to emphasize that this is not totally trivial to show that this concrete description here gives you something in this kfee space. But I like having this concrete description because now it's just this class of rational functions with an integrability condition imposed on it. So, so to prove that if I have one of these satisfying this, that I belong to kfee, how does that go? Well, you have to use some property of p that's non-trivial. You have to use the fact that p is outer. And that lets you do things like say, I know q and p are in H2, and I have an element sign equals. So this function f, q over p, is in L2, and then you need some theorem that lets you say that, well, if I divide something in H2 by something in H2, or the denominator is outer, that I stay in H2. So you have to use a non-trivial property of p, that it's an outer function. And then you have to play around with the formulas to get that that functions of this form belong to kfee, and that's a little easier. But so let's see, what do I have? I have I have the numerator has this degree less than n1, n2. So I can reflect it to get a q tilde. But I have q is fp. And so you do this reflection to fp and you get this formula here. And then I define this function g here, which is q tilde over p, which has this formula right here. And again, I get, this will be p tilde over p, which is my rational inner function, times f. So it belongs to L2. So again, I use this property that p is outer to let me say that I have something in L2 and I have two things in H2 where the bottom is outer. I get that G is in H2. And so I just wanted to emphasize that getting this concrete description is not totally trivial. But now we have this nice space, or somewhat nice space, because we do have to figure out exactly what, when is a rational function in L2 of the 2 torus, but at least we've broken down the problem. Okay, so these are the important Hilbert spaces associated to a rational inner function, and this works for more general inner functions too. And we can use these Hilbert, the kfee space that I wrote down, to actually give another way of characterizing uniqueness of Agler decompositions. And this, you can do this also for more general inner functions. So this phi equal to p tilde over p has a unique Agler decomposition. K1 and K2 are uniquely determined. I already said this part, if and only if p is saturated. So that's a theorem that you need all of the common zeros of p and p tilde to live on the 2 torus. So it has as many singularities as possible. And this turns out to be equivalent to this kfee space being trivial. So this kfee space, which is supposed to be this generalization of a model space, can be trivial. I mean, you can make modifications of the space to have non-trivial ones in general, but it turns out that you get uniqueness when the space kfee is trivial. And so this is building up to the idea that, well, in more general situations, if I want to describe Agler decompositions, well, it turns out the kfee will have to be non-trivial, and you'll have to use that space somehow to help you describe possible Agler decompositions here. Okay, so here is the all-important pair of truncated Toeplitz operators that was promised. So everyone write it down. I'll wait for you to get out your pencils. And here goes. So I have a rational inner function, p tilde over p, and my kfee space. Here is not the commuting pair of truncated Toeplitz operators, but here's the definition I need. Something. The first operator is just this compression of multiplication by z1 to my space kfee. And T2 is the same thing with multiplication by Z2. And these two operators actually, they don't in general need to commute. But you have to really get into the weeds of these spaces and different orthogonality conditions that they possess to see that T1 and T2 adjoint commute. And it's this really bizarre thing where there's this kind of anti-symmetry here, but it's forced on you. And so I can't go through the proof of this because it takes too much work, but you'll have to trust me, and I'll tell you why this pair is interesting because of a bunch of different properties that it has. But it's just this like compressions of two different shifts, but you have to take an adjoint in one of them. I mean, I could talk about T1 star and T2, they commute as well. So, the symmetry, anti-symmetry is balanced by something, but still it's kind of a strange fact. So why is this pair interesting? This pair's invariant subspaces turn out to be in direct correspondence with these minimal Agler decompositions. And I'll give you an illustration of that with like a trivial example in a moment. But it's kind of amazing to me that you can have this pair that if you give me one of their invariant subspaces, I can build an Agler, one of these minimal Agler decompositions out of it. They're also interesting because they have interesting eigenstructure. So the joint eigenvalues of this pair give you some funny things, because of this adjoint in this position. You can't expect the joint eigenvalues to give you something like common zeros of P and P tilde, because P has no zeros in the bidisk, and this is a pair of commuting contractions. So what does it give you? It gives you this oddball thing where I have to do like this partial reflection, and it's not even with adjoints. But I guess that's reflected in the fact that you have an adjoint up here. But the joint eigenvalues of this pair will give you common zeros of this half reflection and this half reflection within the bidisk. So, and that makes the common zeros of these two things. Let's see, I should start with, let me just mention something. So P itself has no zeros in the bidisk, so its zeros are over here, while P tilde is this reflection, so it's, oh wait, I should be drawing, this is the wrong picture. Let me start, okay. So you can draw a diagram like this, where P has no zeros in the bidisk. So if you do this diagram of moduli, P's zeros live out here. And then P tilde zeros live in a reflected region. So the common zeros of P and P tilde will be in these off-center places. And so if I do this like half reflection down here, I move some of the common zeros into the bidisk. And so that at least makes sense that you would get points in the bidisk. And I make a comment here, this would be interesting to generalize to more general inner functions, and I hope somebody's inspired to look into that. And one of the things that I did with looking at this pair is that you can use this eigenstructure to compute the dimension of the kfee space. It turns out to be n1, n2. So n1, n2 is the biggest it could be because the space consisted of polynomials with their degree bounded by n1 and n2. But we also have this L2 condition. And so what you have to subtract off is this like 1/2 of the common zeros of P and P tilde counted with multiplicity. And it turns out all common zeros of P and P tilde on the 2 torus have to have even multiplicity. That's clear intuitively because the zeros have to like come in these pairs. But I'll mention something in a moment that lets you see that using correct mathematics. But these are the reasons I think this pair is interesting. And now let me illustrate at least this first point with the easiest example I can mention. So this is the easiest non-trivial example that I can think of. So I'll take my polynomial to be 1, and it seems like that's too easy, but I can reflect it at a higher degree than p is. So I can make p tilde just say z1 to the nth power, z2 to the nth power, and then phi just becomes a monomial. And you might argue this is too simple, but I think it's even in this case, you can illustrate the theorem, so I think it's worth going through. So the kfee space, there's no denominator, so there's no real like issue of singularities. So I just get span of certain monomials where j and k are less than n. And so here, the space will clearly have dimension n squared. And what is this commuting pair of truncated Toeplitz operators? Well, they're like these forward, like a truncated forward shift and a backward shift in the other variable. So T1, I multiply by Z1 and then project back to this block in H2 of the 2 torus. So a monomial Z1 to the J, Z2 to the K, well, I'll multiply it by Z1, and then if I'm still in the space, which would mean that J plus 1 is less than n, then I can keep it. But if I leave the space, then it has to be 0. So I think of it as like a picture. You have these monomials in this block. This is representing things in terms of their Fourier coefficients. And so if I have a monomial with Fourier support over here, well, it gets knocked out of the block, and so it maps to 0. But other stuff is fine. So a monomial supported here can just get bumped over. Okay, and T2 star, you would shift it down, so no big deal. I'd have Z1 to the J, Z2 to the K, and I'll divide by a Z2 if I can, but if I can't, I just put in 0. So this is supposed to be the easiest non-trivial example, but if you make it too trivial, then you get like you get one joint eigenvalue of the pair. The joint eigenvalue is 0, 0, and you get what you'd think of as a joint generalized eigenspace, which means that for anything in the space, if you apply one of these operators enough, you get sent to 0. So the joint generalized eigenspace associated to it is all of kfee. And I claim that the invariant subspaces of kfee give you all of the Agler decomposition, all the minimal Agler decompositions of this inner function. And I was surprised writing these notes out that you like, what are the invariant subspaces of this pair? I didn't realize that I'd get into like the Catalan numbers, but I guess it's all of the invariant subspaces have to be these sets that I draw their Fourier support, that if I shift the set to the right, I stay within the set, or if I shift it down, I stay within the set. So you get all of these different staircases here, which I guess if you're going to count all of the different invariant subspaces, it's like a Catalan number. So that's interesting, but I didn't realize that until I wrote these notes. But okay, and so let me illustrate how you go from those invariant subspaces to Agler decompositions in an easier non-trivial example where I just pick, say, 3 for this exponent. The way you do it is you take this bigger space, kfee, this like bigger version of a model space, and it does break up into this L-shaped space in terms of Fourier series. And the way you build Agler decompositions using this bigger space, it turns out you can do it by breaking up your space into a piece that's invariant under Z1 and a piece that's invariant under Z2, and you get minimal ones by doing it with orthogonal direct sums. So one way I can do it is to, it turns out all the choice in breaking up the space into these 2 pieces comes from breaking up the kfee portion here, because to get a piece invariant under Z1, I can't play around with this part at all. I just have to play around with the kfee portion. So here's an example of a space that's invariant under Z1. And here's an example of a space that's invariant under Z2. And so if you break up your space into pieces like this, you can write out reproducing kernel formulas that give you an Agler decomposition using the associated wandering subspaces of these different subspaces here. So I can't say too much about that because I wanted to at least mention something about the local theory of stable polynomials. So here's how this would go in that example. I wrote out a particular way of breaking up kphi. So the wandering subspace would have this reproducing kernel. And so you could generate the full space invariant under Z2 by dividing by this kernel. And you'd get a reproducing kernel for that space invariant under Z1 with this kernel. And then you clear denominators and you get these Agler decompositions. So that's a fast version of it. But hopefully you can see somehow that like breaking up these invariant subspaces gives you the different Agler decompositions. So I don't have too much time for Act 3, so I'll mainly just introduce these questions and then stop. So there are lots of things that, lots of questions that this leads to. For a really basic question is why is this intersection multiplicity of P and P tilde even? Because I had this formula for a dimension and we divide this by 1/2. And you could use our local theory of stable polynomials to answer that pretty efficiently. And this topic also brings up just the general question of how do you know when a rational function with one of these denominators is in L2. And so we've built this local theory of stable polynomials that can kind of answer that in some cases very directly. I have indirect ways to do it built out of the reproducing kernel machinery. Okay, and then you also might be interested in non-inner bounded rational functions. And so our local theory of stable polynomials will let you study that question, which we have like something called the numerator criterion conjecture, which Alan may get to in his talk. So these are like the main questions that this leads to, that requires understanding this denominator P and understanding what it looks like near the boundary singularities in detail. And I probably shouldn't go too much further than that, other than just to say, if you want to know more, you have to attend Alan's talk, and I'll stop there. Thank you.
Thank you, Greg. Let's thank the speaker first. Any question or comments for Craig?
So maybe a quick question about these operators T1 and T2 star. So you said it would be of interest to study them for more general inner functions than rational. Do you have any ideas or examples of what what might happen in that situation?
Yeah, honestly, I haven't thought about it. You know, there should be something interesting with their joint spectrum, because you get such like the joint spectrum for the rational intercase. It gives you this really important information. So yeah, I was hoping, you know, to inspire someone or to inspire myself to look at it deeper. I think maybe if I've been meaning to, you know, broaden some of this material to the case of like meromorphic inner functions, where you could have entire functions as the numerator and denominator, and then maybe you'd get interesting joint spectrum in a case like that if you do it in the proper setting. But for more just like a blanket like inner function in two variables, yeah, I don't know.
Any further comments or questions? Not, let's thank Craig again.